Today we're going to talk about quantum computing error mitigation. So the presenters are going to be Aryan Das, me, and Ayushman Bisht.
Okay, so quantum computing has the potential to significantly improve computational tasks. Unfortunately, errors due to outside interactions cause the data to be noisy. Our group is focusing on finding a way to decrease these errors by reverting the data back to what it was before the noise. To simulate realistic errors, we used a bosonic math model on surface code. Then we used both convolutional neural networks for pre-processing and feature extracting, and graph neural networks for predicting and correcting errors in the surface code. By training and evaluating the CNNs and the GNN, we can increase performance in quantum computing. These changes will allow for major developments in the field and will be a significant contribution to making accurate quantum structure. So, what is quantum computing? Quantum computing is a section of computing that combines quantum mechanics with classical computing, employing phenomena such as superposition and entanglement. If classical computing is like flipping a coin, quantum computing is allowing that coin to exist between the states of just heads and tails, revealing almost infinite possibility. In quantum computing, we deal with quantum bits, also called qubits. Unlike classical computing, which is consisted of zeros and ones, quantum computing uses bits in superposition between the states of 0 and 1.
Aryan.
So what is error? Um, so quantum error comes in the form of phase flips and bit flips, and these essentially represent changes in the original qubit structure. So a bit flip is the switching of the two components A and B, which make up the weights of whether that qubit collapses to be either a 0 or 1. A phase flip, on the other hand, is a change of sign of one of these components. Um, to prevent our qubits from being affected by these errors, we use quantum codes, such as the surface code. And the surface code is essentially a lattice or a 2D grid of qubits, which makes it harder for qubits to spread out, and it makes it easier to measure where our errors occur. So error in surface codes spread from qubit to qubit, and the stabilizers that exist in our surface code are kind of used to detect the path along which the error occurs. And so because the stabilizer operators can only detect kind of like individual points, it is up to us to determine the path of the error propagation, kind of like the connecting the dots on the game on the right of the slide. Um, Unlike that game, though, we don't have a set space to fill up, and the error propagation could have taken any path to its destination.
So, as for the solution, our solution is to replicate surface code and use an MWPM decoder, CNN, and GNN pipeline to find and fix the surface code error propagations as fast and as efficiently as possible. So, as for what we've done so far, we've used the QService module in Python to replicate the surface codes accurately. And we are also switching to Qiskit for easier use and better synergy with the Qiskit error prediction models, which have been created by IBM. We've currently made an elementary CNN model to pre-process the data and extract features with predictions for about confidence values for where the errors might be. And then we inputted the CNN outputs into a GNN model, which actually like learns all the connections and like makes final outputs on like where errors are probably going to be. And then together they can find and fix errors into surface code. So as for results so far, with our elementary CNN that was trained on a 2D array, like our best recorded accuracy was 56.2%. So as you can see here, like on the leftmost image is a noisy surface code, which is a surface code with all the errors applied. And the right is basically the matrix with all the confidence values for the like system, which is basically like the probability that the model thinks there's an error there. So the black squares means that there is an error, the white squares means that there isn't an error, and the gray squares means that it's unsure. Currently we're focusing on like increasing the accuracy and implementing the Q service and Qiskit service code like error like application models to make sure it's more accurate.
Uh,
So yeah, you're gonna continue. Yeah.
yeah, so we have some future plans for the project, which includes implementing Qiskit error models now. And we also plan on introducing the current NWPMs into the pipeline. And additionally, we're also looking into other research to find what other methods are also useful to mitigate quantum errors.
All right.
And in terms of timeline of what we've done so far, so this past summer semester, I believe was when this group started. I joined a little after that, but that's when we kind of created information on like how surface codes work and incorporated a bosonic bath model, which essentially is a bath of boson particles on the actual quantum like on the surface code that would interfere with those qubits. And we simulated those codes with a simple 2D array. Um, and then this past fall semester, we've developed our GNN and CNN models, elementary versions of them, and trained them with the simulated surface code and the noise model to evaluate the model's performance. And right now in this early spring semester, we've been focused on fixing our surface code model because our kind of original model of just a 2D NumPy array didn't really have any of the quantum properties inherent. It was really just an array of zeros and ones. Um, and so now we're working on using existing surface code implementations to kind of simulate that error. And we're also working on implementing depolarization error and other error models with Qiskit.
All right. So here's an example of the the new surface code that we're using instead of the NumPy array. So basically when it starts, like it applies the errors. It uses these ancilla qubits which measure like X and Z error. So it just starts like reading the inputs from like those ancilla qubits that measure it. It then like detects a connection. And then with the sample MWPM decoder that's in here that the module comes with, it eventually like applies the decoding like as you can like see on the fifth step pretty much. And then yeah, this is like a comprehensive example of like how the surface code looks like and like how like an MWPM decoder would like work, for example, pretty much. Yeah, so that's the end of the presentation. So we want to thank our advisor, Dr. McMahon, and the ASDRP organization as a whole for allowing us to continue research on this project and basically learn more about quantum computing on the way and like contribute to new developments. And yeah, some inspiration was taken from previous work done on a similar topic by Pranav, Rohan, and Dia. So yeah, thank you everybody for listening. Do you guys have any questions?